Okay, section 3.7, we are going to be going over improper integrals. So some of the things that we're going to be looking at in this section is how to evaluate an integral over an infinite interval, evaluate an integral over a closed interval with an infinite discontinuity within the interval. So somewhere where it's discontinuous, usually when you have like x minus 4 in the denominator. Then use the comparison theorem to determine whether a definite integral is convergent. So we'll be talking about whether something converges or diverges. So first of all, let's look at integrating over an infinite interval. So if we let f of x be continuous over an interval between a to infinity, so now notice when we are putting in our limits of integration, we have infinity in one of the signs. So that takes some different techniques to be able to integrate. We can do it though. So if we have infinity in one of our limits of integration, then what we're going to do is we're going to change that to a t. So see, they change that infinity to a t, and then take the limit as t approaches infinity. So as long as that limit exists, we can get an answer. Okay. Also, same thing if it's negative infinity. If we have an equation from negative infinity to b, then we just take out that negative infinity, replace it with a t, and take the limit as t approaches negative infinity of that integral. Okay, let's see, there we go. Again, provided that that limit exists. All right, so a couple of things right here we want to make sure. So in each case, if the limit exists, so if the limit exists, then the improper integral is said to converge. If the limit does not exist, then the improper integral is said to diverge. Okay, now this kind of brings back some topics that we talked about when we did limits. Back when we did limits, we talked about how if a limit goes to, like the answer of a limit is infinity or negative infinity, that kind of hit into a gray area. Sometimes a book or question on My Open Math would say if it went to a limit infinity, it did not exist. Others said that the answer was infinity or negative infinity. So with your homework for this, if it gives you the option to say infinity or negative infinity as one of the answers, and it will tell you in there, say infinity or negative infinity, then use infinity or negative infinity. If it just says, does this converge or diverge, if you get an answer of infinity or negative infinity, then say it diverges. Because those limits, when they equal infinity or negative infinity, kind of fall into that gray area, and you'll see that on your homework assignment. All right, so let's keep going on. We can also look at limits that go from negative infinity to infinity. So now we have two parts. So what we're going to do is we're going to break up this function and this integral to two parts, and we're going to go from negative infinity to 0, and then from 0 to infinity. Then we'll go ahead and use our previous methods up here, which they have written out kind of down here. So what you're going to do is you're going to take this and break it back up into two pieces using the above mentioned limits. So you're going to have one limit plus the other, and out in front you'll do the limit as t approaches. I used a and b when I broke them up into two separate pieces. So I used a on this integral, b on the next one. So you'll see that as we go through our notes. Okay, example number 1. Determine whether the integral is divergent or convergent. So if we get an answer, it's an actual number, then it converges and we'll give the answer. If we did not get a number, so like if it is did not exist somehow, then we would put D and E on that one. All right. All right, we are ready. So example number 1, we want to determine whether this integral is divergent or convergent. I deleted the really, really long messages that it had on here, but it did say give the answer if it's convergent. So for this one, the problem with this integral is that we are trying to go to infinity. So there we go. So this is the problem right here. We can't do an integral with infinity in it. So what we're going to do is we're going to rewrite it with a limit out in front. So we're going to say the limit as t approaches infinity of the integral from 0 to t. So that's the only thing that we change. We just bring that infinity sign out here in front with a limit, and then put the t in for the infinity sign, and then we have 6e to the negative x dx. Okay, so now we're going to go ahead. This is now something that we can actually take the integral of. We can pull this 6 out in front of the integral sign, and if you remember when we did limits, we can also pull a constant out in front of a limit. So let's pull that 6 all the way out. It's not going to change or affect anything in the limit or in the integral. And then let's write this e to the negative x as no, let's leave it as e to the negative x dx. Okay, so when we integrate this, we've done this enough. I think you're okay not to do the u substitution, but if you need to, what we would do is we would set u equal to negative x, then u would be equal to negative 1 dx. We'd have to divide that negative out. So just remember our chain rule there, that we have to bring that negative out. And then we have the limit as t approaches infinity of the integral of e to the negative x, which is e to the negative x. And we already brought that negative out. And then that's being evaluated from 0 to t. Okay. So we've got negative 6, limit's still there, t to infinity, just keep dragging that limit along. And then we've got e to the negative t minus e to the negative 0. All right, so e to the 0, that is going to be 1. And then e to the negative t, we could rewrite that. I don't want to rewrite all this, so let's just do right here, make that positive. Okay, so it'd be 1 over e to the positive t. So as t goes to infinity, remember when we did these limits, as t gets really, really, really big, and e to that exponent is going to be a really big number. So if that's all happening in the denominator, 1 over a million, a trillion, that's going to be getting closer and closer and closer to 0. So this part of the limit is going to go to 0. So we end up with negative 6 times, because now we've taken these limits inside here, negative 1 is what's left inside those parentheses. Okay, which ends up being a positive 6. So, because our limit exists, it is convergent, and it converges to 6. Okay, I think we skipped an example here, so let's go back to 2. There we go. All right, okay, try that again. Sorry, I think I hit the wrong button. Example number 2. We need to decide if this converges or diverges and find the answer. So from 3 to negative infinity, well, negative infinity to 3 is what we are integrating for. And 1 over x squared plus 1 is our function. So our problem here is, again, we have an infinity in our integration limits. So let's rewrite that, take that negative infinity out. So we're going to take the limit as t approaches negative infinity. Now we're going to replace that negative infinity with a t. From t to 3 of 1 over x squared plus 1 dx. Now we can go ahead and integrate. So this is an arctangent problem. So we're going to have the limit as t approaches negative infinity of t to, well, let's go ahead and integrate it. I think we're ready to integrate on that. The limit as t approaches negative infinity of the arctangent. So it would be 1 over 1 out in front, so we don't need to do anything with our coefficient, and then inside is going to be x over 1, which will just be x. And we don't have to worry about anything for chain rule on that one either. And we are evaluating that from t to 3. Okay, so now we can go ahead and need to evaluate that, plug those values in. So we're going to have the limit as t approaches negative infinity of the arctangent of 3 minus the arctangent of t. Okay, and then if we plug in the arctangent, let me get that up here real quick. The arctangent of 3 is equal to 1.249. So that is all going to equal, keep that limit in there. And that's going to equal 1.249 minus the arctangent of t. Now we need to take this limit as t approaches negative infinity. So if you remember our tangent graphs, our tangent graph would come right through here. So the arctangent is, let me get a different color. It's going to look like this. Okay. And the asymptotes would be pi over 2 and negative pi over 2. So when we move those asymptotes also down here, the lowest it's going to be is negative pi over 2. It's going to get closer and closer and closer to that value. So the arctangent of t, as t goes to negative infinity, is going to go to negative pi over 2. So our final answer for that one, so that plus, so we have two negatives, that becomes positive, so 1.249 plus pi over 2, and that is going to equal 2.8198, and that will be final answer for that one. Okay, for example number 3, it says determine, again, divergent, convergent, give an answer if it's convergent. So this one, you'll notice, has two infinity signs. So we're going to have to break this up into two separate integrals. Ooh, I don't want red, let's do black. Alright, so our first integral, we're going to break it up to, is from negative infinity to 0. Of the same function, so negative 7x to the 4th dx, and then plus the integral from 0 to infinity of negative 7x to the 4th dx. Alright, so now, because we've got infinity in both of these, we're going to have to rewrite this as a limit. So we're going to take the limit as, now I'm going to use a and b this time instead of t, since I'm going to have to use 2 and 1's going to mean, they're going to mean different things. So I'm going to use different variables. So a approaches negative infinity of the integral, so a to 0 of negative 7x to the 4th dx, plus the limit as b approaches infinity of 0 to b of negative 7x to the 4th dx. Okay, so now we're going to go ahead and take our integrals. Our limits are still going to be there, so the limit as a approaches negative infinity. We're going to add 1 and divide by that number, so negative 7/5 x to the fifth